This is the video lesson for solving more Newton's second law problems. The learning target for this lesson is, I am learning to use Newton's second law to solve AP style and real-world problems. The success criteria for this lesson are, I can use Newton's second law to solve real-world problems, and I can use mathematical reasoning to solve AP style Newton's second law problems. Okay, so let's do a quick Newton's second law review. So Newton's second law is written as sum of F is equal to ma. So the sum of F is equal to the sum of forces, m is equal to the mass, and a is equal to acceleration, where acceleration is equal to the change in velocity over the change in time. So if we write this in terms of acceleration, we have the sum of forces divided by mass, or the net force divided by mass. So again, if we increase the mass and the force stays the same, the acceleration is going to go down. So if we want to maintain a constant acceleration, assuming that the mass is increasing, then the force has to increase as well. Okay, let's look at example number 1. If the rocket sled shown at left starts with only one rocket burning, what is the magnitude of its acceleration? Assume that the mass of the system is 2,100 kilograms. The thrust is in newtons, which was figured out in an earlier example to be 26,000 newtons. This is not an example that we worked, it was in the book. And the force of friction opposing the motion is known to be 650 newtons. Okay, so we want to know the acceleration. So the equation for acceleration is equal to the sum of forces divided by the mass. So let's draw a free body diagram here first. So we have the gravitational force, which is mg, which is equal to the mass, which is 2,100 kilograms, times g, which is 10 meters per second squared, or newtons per kilogram. So that equals 21,000 newtons. So our normal force is also equal to 21,000 newtons. Our thrust is equal to 26,000 newtons. And then our force of friction is equal to 650 newtons. Okay, so let's do sum of forces in the y direction is equal to 21,000 newtons minus 21,000 newtons. And that's equal to 0 because there's no acceleration in the y direction. Then we'll do the sum of forces in the x direction is equal to, so we have, I'm going to write this out, so we have the force of thrust minus the force of friction, and that's equal to the mass times acceleration. So we have the thrust, which is 26,000 newtons, minus the force of friction, which is 650 newtons, which is equal to our mass, which is 2,100 kilograms, times the acceleration, which is what we're looking for. So 26,000 minus 650 divided by 2,100 kilograms gives us our acceleration. So our acceleration then is equal to 12.1 meters per second squared. Okay, so remember, we want to draw a free body diagram, make sure that we have all the forces accounted for. We're going to do the sum of forces. Now, you don't necessarily have to do the sum of forces in the y direction if you know that they're balanced. I just did it here to make sure everything is very explicitly drawn out. And then you do the sum of forces in whatever direction you're looking for the acceleration in. So in this case, in the x direction, and then you work out all of your numbers, and in this case, you're solving for acceleration. Okay, example number 2. A mass of 2 kilograms is suspended from the ceiling of an elevator by a rope. What is the tension in the rope when the elevator, 1, accelerates upward at 1.5 meters per second squared, and 2, accelerates downward at 1.5 meters per second squared? Okay, so let's draw a free body diagram first. Okay, so we have Fg, and we have the force of tension. All right, so our Fg is going to be m times g, so that is equal to 2 kilograms times, now we can write g in different ways, so we can write it as 10 newtons per kilogram. So when you multiply this out, the kilograms divide out, and we're left with 20 newtons. And so our tension force is unknown at this point. Okay, so we're doing sum of forces in the y direction. We don't know in the x direction, or there are no forces in the x direction. So our sum of forces in the y direction are going to be tension force minus the gravitational force, and that's going to equal mass times acceleration. So we're trying to find the tension force. So we have tension force minus the gravitational force, which we know is 20 newtons, and that's equal to our mass, which is 2 kilograms, times our acceleration. Now for 1, we have an upward acceleration, so that's a positive acceleration of 1.5 meters per second squared. Okay, so our Ft is equal to, so Ft minus 20 newtons is equal to, so that is 3 newtons. So our tension force then is equal to 23 newtons. So this would be for part I. So let's move over here and do part II. So we have the same sum of forces, except now our acceleration is different. So we have Ft minus 20 newtons is equal to 2 kilograms times minus 1.5. So we have Ft minus 20 newtons equals minus 3 newtons. So Ft now is equal to 17 newtons. Okay, so depending on whether the elevator is accelerating upwards or downwards, we end up with different tension forces. If the elevator were moving at a constant speed, the tension force would be balanced by the force of gravity, and there would be the tension force would be the same as the force of gravity. All right, example number 3. A person is riding in an elevator. So we got another elevator problem. These are great for exploring Newton's second law problems. So at time t1, the elevator is accelerating downward with a magnitude of minus 2 meters per second squared. A short time later, at time t2, the elevator is accelerating upward with a magnitude of 2 meters per second squared. The ratio of the normal force exerted by the elevator, so we're talking about normal force here, the normal force exerted by the elevator on the person at time t1 to that at time t2 is most nearly. All right, so again, we're going to draw a free body diagram. So we have Fg is equal to mg, which is equal to our mass, which we don't know, doesn't matter. So we know that we can say that we have 10 newtons per kilogram times m. And so our normal force is what we're looking for. Okay, so let's do downward acceleration first. So if we do our sum of forces in the y direction, we have our normal force, it's pointing up, so it's positive, minus our gravitational force, and that's equal to mass times acceleration. So we have our normal force minus 10 newtons per kilogram times m is equal to m times, and our acceleration is minus 2 meters per second squared. Okay, so let's go ahead and add our gravitational force to the left side, or to the right side. So we have Fn is equal to minus m times 2 meters per second squared plus m times 10 newtons per kilogram. So we can factor out our m there. So these units are the same, meters per second squared and newtons per kilogram. So I'm actually going to write this, I'm going to change this to meters per second squared. Okay, so we can factor out the m. So we have Fn is equal to m times, we have 10 meters per second squared minus 2 meters per second squared. So we have Fn is equal to 8 meters per second squared times m. So I've done a little bit of shenanigans here with the algebra. So let's just take a look at this. So I multiplied this negative outside first. I added this to the right side. Okay, so that's why I have a negative outside here, and that's why this is positive. So then when I pulled the m's out, I factored out the m's, I went ahead and moved this 10 to the front, and the negative, I put the negative back inside the parentheses and moved it to the back. So I did 10 minus 2, so that's 8, and then I just put the m at the end. Okay, so let's look at upward. Okay, so I've got the same sum of forces, but I'll write it again. Is equal to Fn minus Fg, and that's equal to ma. So we have Fn minus 10, and I'll do this in meters per second squared the first time, so we don't have to change units, times m is equal to, now this time we have a positive acceleration. So we have 2 meters per second squared times mass. So now I'm going to add this 10 meters per second squared times m to the right side. So we have Fn is equal to 10 meters per second squared times m plus 2 meters per second squared times m. So factor out the m, add the 10 plus 2, so we have the normal force is equal to 12 meters per second squared times m. Okay, now what they want for this, for the answer here, is the ratio of the normal forces exerted on the by the elevator on the person at time t1 to that at time t2. So our normal force is 8 to 12. So we have 8 to 12, which we can reduce. So if we divide both sides, of the ratio by 4, so divide by 4, what we end up getting is 2 to 3, which is A. All right, example number 4. A block of mass 2 kilograms is suspended from a rope as shown above. The tension in the rope is 10 newtons. The acceleration of the block is most nearly. Okay, so time for a free body diagram. So our first force is always the force of gravity, mg. So we have m is 2 kilograms. G is 10 newtons per kilogram, which is equivalent to meters per second squared. So that is going to give us 20 newtons. And then we have this tension force, which is equal to 10 newtons. All right, and we want to know the acceleration. Okay, so let's do a sum of forces. So sum of forces in the y direction, we have 10 newtons minus our, let's rewrite this. So we want the tension force minus the gravitational force is equal to mass times acceleration. So our tension force is 10 newtons minus our gravitational force of 20 newtons is equal to 2 kilograms times our acceleration. So we have minus 10 is equal to 2a. So a then is equal to minus 5 meters per second squared. So E is the correct choice, 5 meters per second squared down, because the minus tells us that the minus is directionality. So the minus is telling us that the block is accelerating downward. All right. All right, so what have we learned in this video? So we learned to use Newton's second law to solve problems. So if the object is accelerating, the force is equal to mass times acceleration. And we learned about using mathematical reasoning. So read the problems carefully and determine what it is asking for. All right, everybody. Thank you.